let V and W be vector spaces over some common field F. Shared field F. A function F V to W is a linear transformation from V to W if for all uv in the domain vector space and for all A in their shared field, we have that this function is a group homomorphism, preserves addition, and secondly, that it preserves scalar multiplication. And we had a couple of other equivalent characterizations to that. So instead of those two, I could have written f of cu plus v equals c f of u plus v. Or I could have written f of sum of the ai vi equals sum of the ai f of vi. So I could have written that. I could erase it and instead write this condition, or I could erase that and instead write that condition. That would all give me the same definition. And we talked about how it preserved properties that you would expect, like f of the zero vector is the zero vector. That's in V and that's in W, and so on. And most of what I want to talk about today is composition. We had also, addition and scalar multiplication. But I want to think about composition. So suppose I have F, which goes from V to W, and I have G, which goes from W to, actually, let me change these so that, I'm sorry. Let's do it this way. F from U to V, and G from V to W. So I like to draw these little diagrams. F goes from U to V, and G goes from V to W. Yeah?
Could you explain why f of cu plus v looks like that cf of u plus v?
When you could apply these two rules.
Or shouldn't that be f of v?
Oh, yeah, I'm sorry. Yeah, that's right. Okay. So the idea is that if the codomain of one function and the domain of the other match up, of course, if these are just set functions, I can always compose them. As functions, just functions, not linear transformations, to define F composition G. And how is F composition G composition F defined? As just a function of sets. I mean, we just define it by saying you apply F and you apply G, right? G of F of V. Now, can we compose F and G as linear transformations? what should we mean by that? Or what do I have to check about this thing in order for it to be a sensible definition of composition of linear transformations? You think about this as being like a guess, right? So we have these two things which are linear transformations. And we know because there's this sort of sequence of pieces of structure. First it's a set, then it's a vector space, and so on. We know that at the bottom there's functions, and we can compose the functions. But what we don't know a priori is that what we get out, G composition F, which is a new function defined by telling you where it sends each element V in the vector space, big V. We don't know if this is itself a linear transformation. So in order to check that this is a sensible definition of composition, we just need to check that that's a linear transformation. If F and G are linear transformations, then G composition F makes sense, meaning that the middle matches up. Then G composition F is a linear transformation. And it won't surprise you that it is. So what we're trying to show is that it satisfies one of these definitions I just erased, right? Like Cx plus y equals, or no, does that equal C of G composition F applied to x plus G composition F applied to y for some constant Cx and y. I mean, that was one of those three equivalent definitions, and this is the one that somehow has the fewest symbols, and this would be easiest to check. And so in this case, we can do that by just computing, right? So this thing, by definition of composition, the definition of composition that we chose, that we propose, this is equal to G of F of Cx plus y. And then by linearity of the first function f, I can push f through the scalar multiplication and the addition. That's equal to G of Cf of x plus f of y. And then by linearity of G, I can push G through. That's equal to C G of f of x, whatever f of x is, plus G of f of y. And then by definition of composition, that's equal to this thing. C of G composition f of x plus G composition f of y. So that's just a competition. Just a computation. Now, this operation of composing functions or of composing linear transformations is a little bit like multiplication, right? More than a little bit like multiplication, in fact, because if you think about, suppose f is a linear transformation from a one-dimensional vector space to a one-dimensional vector space. And for a one-dimensional vector space over a field, we can write f, right? So how would you characterize a linear transformation that's one-dimensional? Yeah, it's scalar multiplication. By some element of the field. So in fact, this notion of composition is multiplication in the case of one-dimensional vector spaces, and in the case of higher dimensional vector spaces, it's something which is a strict generalization of multiplication. The difference is that for greater than one-dimensional vector spaces, the composition is not commutative. So in some sense, that's totally obvious, because so in this case, this was a map from a vector space to itself, but right, in general, I can have this kind of situation where I have a map F, which goes from vector space U to a vector space V, and a map G, which goes from a vector space V to a vector space W. Then G composition F makes sense, but not only is F composition G not equal to G composition F, F composition G is not even defined. It doesn't make any sense because there's no set in the middle. G goes from V to W, F goes from U to V. F doesn't know what to do with things from W. Right? Makes no sense. But even when they do match up, suppose that F and G are both maps from a vector space to itself, as long as that space, it's possible that they commute, but in general, they don't. So this is sort of a non-commutative multiplication. And the other thing, or one of the things to note about multiplication is that there's a special element. When you think about the field and you think about multiplication in the field, there's a distinguished element that has a special role in multiplication, right? What's that element? There's an alpha in the field such that for all x in the field, alpha times x is equal to x. Okay. What's that called? It's called 1, the identity. So if we want this to be like a multiplication, we expect that there's also some sort of identity, right? Some sort of special function f or g, so we want some kind of identity, and that identity is going to have to depend on the vector space that we're talking about, which is a map from a vector space to itself, such that if f, say, goes from V to W, we want first applying identity V and then applying F. Picture identity V is the same as just applying F. And on the other side, if I apply F, which goes from V to W, I should put some letters here, VW. Now I want the identity on W. F goes from V to W, and identity W goes from W to W. We want identity on W composed with F also to be equal to F. And of course, that in the case that V and W are equal, these two things will be equal. V will equal IW, ideally. There's kind of many ones. There's a 1 for every vector space, just like there's a 1 for every field. So we want this to be true, right? And over here, we want this to be also equal to F. So what should this identity be? We don't have any bases yet, so we can't talk about a matrix. So how can I define this identity linear transformation? Or even, make a proposal that's a set function, and then we can check that it's a linear transformation. Ideas. So if I just want a set function, let's let V be an element of the vector space V. The identity on V should take this V, this little v, and spit something out. What should it spit out? I can certainly define a set function by telling you what it does for every element of the set. Right? How about in this other example we had? So we had the category of relations. So A and B are finite sets. A relation is a subset of those. There's a notion of composition that we talked about, right? How to combine two relations. You just take all pairs such that there's a pair in the middle. So if I have a relation R, and I have a relation S, and I have sets A, B, and C, which are finite sets, the composition, S composition R, is the set of all pairs, something in A and something in C, such that there exists something in B that AB is in this and BC is in S. Right? So that was the composition rule. And I claim this also has an identity. So there's an identity relation, something I can compose with any other relation and get back the first relation. How about the identity relation? So the identity relation has to be a subset of the Cartesian product of a set with itself. Let's call it I sub A. That's a relation which is a subset of that. So suppose A is equal to 1, 2, 3, and this A is also equal to the set 1, 2, 3. What's the identity? Makes sense. It would be the identity matrix, right? So thought of as, so the identity A in this relations set, finite sets and relations setting, is just going to be pairs, let's call it AI comma AI, such that AI is in A, which in this case, I can write this as a matrix, 1, 2, 3, 1, 2, 3. Actually, let's write it two different ways as a matrix. In this Boolean semi-ring I was talking about, if I want to be explicit, what the pair 1, 1 is true, the pair 2, 2 is true, the pair 3, 3 is true, and all the other pairs are false. They're not in the relation. If I compose that with any other relation, it's just going to copy whatever's on one side of the relation, right? And I could write it also as a matrix if I think of these things as being zeros and ones. So for example, if my relation was, 1a, let's not use a, 1x and 2y, and I compose on this side with this identity, the rule is I take 1, 1, 2, 2, and 3, 3. That's my relation, which is the identity relation on A. I go x1, there's a path from x to 1 and to 1, and there's a path from y to 2 and to 2, and there's nothing else. So it just gives me back this original thing. Okay. So it so happens that this particular relation is also a function, right? Because for each input, it has an output for every input, a unique output for every input. What is it as a function? I kind of think about it as a function from, this happens to be a function from the finite set A to A. What function is that? I think of it as a function. It takes an element, and it spits out another element of A. the one that corresponds to it. A, again, right? It's the same rule here. So there's just a lot more elements. Now there's infinitely many elements, but the identity function for the vector space V is going to be the thing that takes an element of V and spits out, well, whatever I put into it. That's the proposal. We know that that plays this role of identity under composition of functions. If I compose any arbitrary function on one side with the function which does nothing, which just gives back what I started with, I get back the function. And that's true here. So it does do this. It solves this equation, right? It solves this equation, but there's one more thing we have to check. What's that? We have to check that it's linear. It's the thing that solves that equation, but it's not clear yet that it's linear. So how do we check that it's linear? Just use one of those axioms for being a linear transformation. So let's say ID of CU plus V. Well, by definition of the identity function, that's just CU plus V. And again, by definition of the identity function, I can replace U with ID times U, ID of U. And I can replace V with ID of V. Okay. And that's what we wanted to prove, right? That shows that it's linear. So that solves the, so let me say a word about it. So I'm going to use throughout the rest of the class these little diagrams to keep track of vector space, which vector spaces are which and which functions are which. You can go very far into these things, and they're actually quite useful for lots of purposes. And we're going to slowly build up some shorthand. You don't have to worry about it. If it doesn't help you, you don't have to think about it very much, but I find it very helpful. So we know how to solve this equation for a function. So how about if we just think about the diagrams? Is there a diagram, like a smaller diagram that I could plug in this box that would solve this equation? Just a line. Yeah, that's right. So we use just that. We could write it ID, or we could just write V for this identity in V. Because then it's sort of literally true in this diagram that F ID, we want that to be VW. If we choose just the line with an arrow inside, that's equal to that, which is what we wanted. By some sort of graphical rule, which you can make into something that's a formal idea, but we're not. We're just going to use it as kind of a heuristic. Okay, so that's the symbol for that. And one of the other nice things about this this graphical thing is it helps you remember. So it helps you remember the identity axiom, right? What the role or the equation that the identity linear transformation solves. There's also another property of composition, which is that it doesn't matter what order I do it in not in the sense of commutative, but in the sense of grouping. So if I have 3 linear transformations, F, G, and H, and they go from vector spaces U, V, W, and I don't know, Z. I can write this as H composed with G composed with F, or I could write it as H composed with G first and then composed with F. And either way, I get the same answer. Right? That's just a property of functions, and so it's a property of linear transformations. what's this property called? We've seen it before. It's associativity. Yeah. And one of the things that's nice about the diagrams with this symbol for the identity is that not only does it satisfy these identity equations, it also is automatically associative because we just draw the same picture for both of these sides, both sides of this equation. It doesn't know about parentheses. Okay. All right, so another reason that it's convenient. Okay, so let me. I have one more thing that I kind of want to talk about, but let me pause for a second to see if there's any questions or confusion about what we've talked about so far. It's a little abstract. It'll get more concrete as we go on. Okay, so we have these properties of identity. There being an identity, there being an associativity. And those two things are true for many, many mathematical objects. Almost anything you'd encounter has that structure. All of the groups and monoids, parts of our rings and vector spaces and stuff has that. And there's more properties for vector spaces and linear transformations because they're very nice. So one of the other ones is that they have a distributive property. So to keep track of where we are, let's say we have U, V, and W, 3 vector spaces. And we have 3 maps. We have F, F1, and F2 that go from U to V. We have G, G1, and G2 that go from V to W. In other words, F, F1, and F2 are all linear maps from U to V, and G, G1, and G2 are all linear maps from V to W. Then it's true that we can form compositions like G composition F or G1 composition F2 or whatever, right? And it's true that G1 plus G2 composed with F is equal to G1 composed with F plus G2 composed with F. And it's also true on the other side, G composed with F1 plus F2 is equal to G composed with F1 plus G composed with F2. So this is called a distributive property for linear transformations. You can multiply them over sums. Of course, to be able to make sense of that, we have to know how to add 2 vector spaces, 2 linear transformations. We talked about that last time, but let me remind you. So the space of linear transformations from V to W is itself a vector space. It has an addition. Well, let's make it F1 and F2 just to be consistent. G1 and G2. G1 plus G2. The definition of addition in VW comes from addition in W. We know how to add vectors in W, so we just say for anything in V, we define this to be G1 of V plus in W, G2 of V. And in and scalar multiplication, A times G1 or G of V is equal to A times G of V. So here the scalar multiplication happens in W, and here we're defining scalar multiplication in the vector space of linear transformations. And then we had a 0 element. That was the vector. That was the linear transformation which takes every vector in V to 0 in W. Okay, so let's look at this for a second. So where does this addition happen? Which vector space? G1 plus G2. Yep, that's L of VW. How about this addition? L of UV. This one. UW. So this one, I've composed F and G, so it goes from U to W. And how about this one? It's the same. That's right. It's also L of UW. So there's a lot of vector spaces floating around here. 3 vector spaces of linear transformations. 3 spaces of 3 spaces of linear transformations. This one, and that one, and 3 underlying vector spaces. So there's a total of 6 vector spaces showing up in this property. Getting crazy, right? Everything's a vector space. Uh-huh.
Because after you do those 2 linear transportation, you got an element in W, right? So that will be 2 vector in W add up together. That's not like any addition in linear transformation. Oh, you're not working on any vector?
Yeah, there's no vector, right? So. No, it's confusing, right? I mean, this thing is defined in terms of what it does to you. But there's no vectors appearing here right now. Yeah. Okay. So we'll see lots more about this later, but I just want to say a couple of words about what's going on with bases. So suppose I have a linear map from V to W, linear transformation from V to W, and I have a basis. For V. And I think about where I just look at, I apply my map to each element of the basis. So I define W1 through Wn to be the image of each of those n basis vectors for V. Then for any vector in V, I know where F sends it, right? Why is that?
after it's defining a linear transformation from V to W.
Yeah, I think, okay, so the idea is if it's, because this is a basis for V, whatever I chose, for the vector space V, whatever vector I choose, I know I can always write it as a linear combination of elements in this basis times field coefficients. But f is linear, so I apply f to both sides of this equation. And remember this, one of the characterizations of being linear is to say that I can push f through any sum, I can push it through any scalar multiple. So that's equal to the sum from I equals 1 to n of ai f of vi. And we took a name for f of vi, which was sum from I equals 1 to ai wi. Another question is, are these wi's a basis for w? Well, it turns out that only for a very special type of linear transformation is it true that this is, so not in general. In fact, I have total freedom to pick these w's. If I start with a basis, I can send each basis element anywhere I like. In fact, I could send them all to the same vector. I could send them all to 0, and I'd still get a linear transformation. In fact, we saw that linear transformation already, right? 0 sends all these basis vectors to 0. And the list of zeros here is definitely not a basis. So I have quite a lot of freedom. And this is all the freedom I have, though. Once I've chosen where each basis vector goes, where every other vector in V goes is absolutely determined for me because of linearity. So though we've seen a couple definitions of linear transformations now, specific linear transformations, so we defined two very simple linear transformations. This one, which sends everything to 0, and this one, which sends everything to itself. To define those, we didn't have to say anything about a basis. Right? And there's other transformations that you can think about defining, like in terms of these. Right? I could scalar multiply this and that kind of thing. But for the most part, when we're defining a linear transformation, we're going to use this fact. So we're going to have a basis for the vector space, and we're going to define linear transformation by saying where it sends each basis vector. In some sense, that plus taking a basis for W, is the idea behind representing linear transformations as matrices of numbers, which we'll explain.